Hello, everyone. This is Mr. Taylor with Young Engineers of Today. Last class, we discussed work and power. All right. And we did some practice equations with those, and we started going sort of the basics of simple machines. Let's review mechanical advantage. Mechanical advantage is the ratio of output force divided by input force, and the output force is bigger than the input force machine has a mechanical advantage. All right. And this equation looks as output divided by input. It's useful to think about a machine in terms of input force, the force you apply, and the output force, which is applied to the task. When a machine takes a small input force and increases the magnitude of the output force, once again, we get our MA. Now, trade-offs. No machine can increase both the magnitude and the distance of the force, one or the other. Now, let's look at this. We have ideal and actual, okay? Now, ideal is theoretical output force divided by theoretical input force. But it's not that simple. We have actual output force and actual input force. This is why. The difference is caused by friction, flexing, gravity, etc. When we take the basic measurements, we're not actually calculating taking in consideration on what we're doing right now is such as friction of a material or flexing. But when you actually put those in to the calculation, now you're getting the actual MA. Here's an example practice problem. Go ahead and answer that. What is the mechanical advantage of a lever that requires an input force of 20 newton lifts an object that weighs 60 newtons? You get a mechanical advantage of 3 using the math equation above. Let's do another one. Amanda uses a wheelbarrow to lift a load of bricks. The bricks weigh 600 newtons, which is more than Amanda could normally carry. However, with the wheelbarrow, Amanda can lift the bricks with as little as 120 newtons. What is the mechanical advantage? She got 5. And lastly, Marshall wants to remove a tree stump from the ground. To do this, he puts one end of a log beam under the stump and puts all of his weight on the other end. His weight is just enough to lift the stump. The stump weighs 400 newtons. Marshall weighs 250 newtons. What is the mechanical advantage of the lever Marshall is using? You should get 1.6 MA. Okay. Now, we went over inclined plane last class, which we know we get an ideal mechanical advantage by the length divided by the height. Here are some examples. Here are some more examples that we typically don't think of. Then we went into a wedge last class. Here is the ideal mechanical advantage. And you're looking at the length versus that thickness area. All right. Here are some examples. Fork and a knife, screwdriver, golf club. Here are some others that we typically don't think of, such as nail, teeth, ship. And then last one we went over the previous class was a screw. Here is the IMA formula, and let's look at that a little bit more simplistic light. Mechanical advantage of a screw can be calculated by dividing the circumference by the pitch of the screw. Pitch equals 1 divided by the number of turns per inch. And basically a screw, which is really cool, is an inclined plane wound around a central cylinder. Now you're going to start noticing that a lot of simple machines are related to one another. They're built upon each other. Now here are some examples of screws. And here are some other examples that we see on a daily basis that we don't always think about. Now, levers. A lever is a rigid bar that rotates around a fixed point called a fulcrum. The bar may be either straight or curved. In use, a lever has both an effort or applied force and a load, which is a resistance force. And sometimes these are considered input or output. All right. Now, basically we have 3 types of levers we're going to be looking at. All right. And they're all levers are determined by the location of the effort force and the load relative to the fulcrum. Okay. This is a first class lever. Okay. Here's another way of looking at it from an effort and resistance standpoint. Some examples. All right, here's a second class lever. A little bit different, input, output. Here's a way of looking at it from a resistance effort standpoint. Wheelbarrow, nutcracker. All right. Doors, because they're on a hinge, and they're both going in the same direction. Tweezers, because the fulcrum is on the other side, and output and input going in the same direction. There's a way of looking at that from a resistance standpoint, an effort standpoint. All right. And then some examples of this: tweezers, arm, hammer, shovel. Okay. We went over and answered these by determining which one of these were in class. And there's the formula, a little bit complex for you older students. Now, some other examples. Here are a few more. Now, wheel and axle. Now, wheel and axle does have an ideal mechanical advantage. Wheel and axle is a simple machine consists of a large wheel rigidly secured to a small wheel or shaft called an axle. Neither the wheel or axle turns, the others also turns one full revolution, or either part causes one full revolution of other part. Fan blades are attached to the wheel. When the axle turns, fan blade spins. Mechanical advantage of the wheel and axle is the ratio of the radius of the wheel to the radius of an axle. So basically, you change the radius by one being bigger or smaller. Okay. Now we can attach gears to these, and now you can change the direction which a gear moves, and it just helps us get and keep improving and building upon our simple machines. Here are some examples of wheel and axles. Here are a few more, and we might not think of or really notice day to day. Now, the last simple machine we're going to look at is pulleys. Pulleys are technically wheels and axles with a groove around the outside. So they are wheel and axles, but they don't really become pulleys until we put a rope, chain, or belt with that hook into that groove. So there's that relationship we talked about earlier. Pulleys consist of three types. A fixed pulley. It does not rise or fall with a load being moved. A fixed pulley changes the direction of a force, however, it does not create a mechanical advantage. A movable pulley rises and falls with a load that is being moved. A single movable pulley creates a mechanical advantage, however, it does not change the direction of the force. Mechanical advantage of a movable pulley is equal to the number of ropes, and they get more complex. And compound pulleys are a mixture of fixed and movable. A pulley can be used to either change the force or gain mechanical advantage. As examples of both of these here. There's a little bit more on fixed and movable, as well as combined pulleys. Okay, and one thing to point out, effort needed to lift the load is less than half the weight of the load. The main disadvantage is that it travels a very long distance. Okay, and there are some examples. Excuse me. And then here are some more. Now, when we talk about efficiency, one thing I want you to take away from this is that our output forces, some of it is lost due to friction. We talked about this earlier. So no machine will have 100% efficiency due to friction. Now, when you start combining simple machines, you get complex machinery. And some of these ancient weapons here, you can start noticing there's a wide mixture of simple machines, such as in the trebuchet. You can see a pulley, you can see a wheel and axle, you can see a lever. All right. On this type of arrow crossbow device, here you can see a wheel and axle, for example. You can see a pulley. Okay. All right. Then we took some time, played the simple machine game. All right, there's the link below. Then we looked at some ancient technologies. Damascus steel, super strong, cut through lesser swords, kept an edge, less sharpening, flexible as well, as strong. Now you're starting to look at like what we would consider materials engineering, mechanical engineering. You're doing a lot of things to improve this process. Then we looked at Roman concrete. We have evidence of this because it's lasted over 2,000 years, things that have been made out of concrete. We know the ingredients, but here's the sad part. We try to make it doesn't not turn out as well. One of the many technologies lost in the Dark Ages. Throughout time and history of humanity, we've lost, discovered, lost again, rediscovered things due to disease, due to human greed, due to wars, etc. That, and this is a great example. We lost concrete, and it's a lot to say. What else? How far we would have been if certain things wouldn't have took course, such as like the Black Plague. Because we went back, we moved backwards. We went from having things made out of concrete to going back to building things out of stone. All right. Now, Greek fire. Ancient Greeks made napalm. We reinvented it in the 1940s. Napalm, highly flammable, and just burns high temperature. And yes, this is a guy in the image using a flamethrower. Okay. All right. Here's some more. The Hero steam engine, and this link here. Let's go ahead and click on that, just so you can see part of it.
This is for the makers, the ones who endlessly imagine new ideas, new
All right. All right, so Hero Heron worked at the Library of Alexandria. He was a writer, engineer, and scientist, but he made a steam engine. He may have invented the first robot powered by falling weights. The thing about this is steam power didn't really become extremely significant again until like the 1800s with boats and trains. So, very impressive. I mean, you can think of all the technological advantages of using a steam engine here, especially at the time of Alexander in ancient Greece. All right. Now, next, we have the Baghdad Battery, produced weak current using religious ceremonies and gold plating processes. Then we had the Roman cup. Added light and the glass changes color using nanotechnology, change color, grinded gold and silver in flakes. And then the Viking compass, accurate as a modern compass, navigate low light and fog. It's like a prism. Use crystals to amplify existing light. Okay. And then we have evidence of natural gas lines in ancient China. And then there's other things that aren't true, such as South American airplanes, spark plug from 500 years old rock, not true, and ancient astronauts. This is almost like pseudoscience. Okay. Thank you, everybody. Take care.